Hello everybody and welcome back. Today we are going to be talking about plate boundaries. We're continuing with our plate tectonics unit and today is lesson 3. So as always, you should have downloaded your interactive notebook pages for the day, and this lesson will correspond with those guided notes. So last week we talked about Alfred Wegener and how he noticed that the Earth kind of had these different sections of like crust that were moving around. And remember, he had a few different pieces of evidence for something called continental drift, which is basically he just noticed that the continents were moving, right? So he thought that there was one large continent a long time ago called Pangaea, and eventually it broke apart and they moved away from each other to give us the continents we know today. Well, now that we know that there's evidence for plate tectonics and the movement of plates, today we're going to talk about what actually drives that to happen, and we're going to talk about what happens at different plate boundaries. So the first thing we're going to define today is a plate boundary, and this is just when the plates, so what a plate is, it's the part of the lithosphere that's broken into these chunks of crust that float or ride on the asthenosphere. And remember, the lithosphere is the rocky upper part of the Earth, and then the asthenosphere contains the mantle with that really hot molten part. Okay, so the plates float around on top of the liquid form of the mantle, and they will move away from each other. There are 3 types of plate boundaries we need to know about. So sometimes these plates that are broken up will come into contact with each other, or they'll move away from each other, and we have to know what happens when that occurs. So the first type of boundary we're talking about is a divergent boundary. If you diverge, you move away from something. So in a divergent boundary, 2 plates move away from each other. So 2 plates move away in opposite directions from each other. As the plates move apart, the magma will rise from the mantle. It will fill in space between the plates, and then it will harden. These are mostly found on the ocean floor, and features include ridges and rifts. And examples of this are the Red Sea, the Mid-Atlantic Ridge, the East African Rift Valley, and others. So when we think about these plate boundaries, what we have to know, you guys have to know the difference between them, what direction the plates are moving, what kind of land formations happen here, and then also some examples of each. So here the land formations would be the ridges and rifts. An example would be the Mid-Atlantic Ridge or the Red Sea. And then the movement of the plates are away from each other. And these are just the steps of Rift Valley formation and mid-ocean ridge formation. So if we look, these arrows are showing us where the plates are moving. So these 2 plates are moving opposite of each other. The magma comes up from the mantle and fills in the space as the plates move away. And then crust will form, and eventually these mid-ocean ridges will form. So we have this kind of uptick of the magma that eventually cools into new crust, and it will form a mid-ocean ridge. The Red Sea is an example of this too. So here where we see these 2 plates are moving away from each other, and as they move, a ridge will form, and eventually it will be filled with water. The next boundary we're going to talk about is a convergent boundary. So if you diverge, you move away, but if you converge, you come together. So a convergent boundary is the collision of one plate with another, and there are 3 types of collisions. So you need to be able to distinguish all 3 of these. So we've got continental oceanic, continental continental, and then oceanic oceanic. So in a continental oceanic convergent boundary, this means that one oceanic crust or one oceanic plate collides with one continental plate. Okay, so the plate beneath the ocean collides with the plate on the land. Okay, oceanic crust is denser than continental crust, which basically just means it's heavier. So when they come together, what happens is because that oceanic crust is denser and heavier, it will go underneath the continental crust. So it will be subducted beneath. So this forms something called a subduction zone. And this refers to the region where one plate moves under another. And again, if we've got continental and oceanic crust colliding, the oceanic crust is going to move under the continental crust. Okay, Oceanic always subducts under continental. And features here include volcanoes on land and then trenches offshore. So examples of these are in South America and Nazca, we've got the Andes Mountains, and then there's also something called the Peru Trench. So here's an example of this. So again, here we've got our oceanic plate beneath our ocean, and then we also have our continental plate. So the continental crust is on land, the oceanic crust is beneath the ocean. So as they collide, so as they move towards each other, this oceanic crust is denser. So here we've got our subduction zone. This crust gets pulled beneath the continental crust. Okay, and as this movement happens, we have magma that's forced up, and we will eventually get volcanic arcs. So we'll get volcanoes here, and then offshore in the water, we will get trenches. Okay, so continental oceanic boundaries lead to trenches offshore, and then volcanoes on land. And again, this oceanic crust is subducted beneath the continental crust. The next one we have is a continental convergent boundary. That means two continental plates, so two land plates, are meeting each other. So the colliding edges are crumpled and then they lift up to make mountain ranges. Okay, so when you have a continental convergent boundary, you will get mountains. Neither of the crust will subduct because continental crust is equally dense, so one will not be subducted beneath the other. These are not volcanic. Okay, so volcanoes occur where there's a subduction zone, so we will not get volcanoes with a continental convergent boundary. Okay, so examples are here in North Carolina and Africa. We've got the Appalachian Mountains. So if you guys have ever been to the mountains of North Carolina, you are in an area where two continental crusts are colliding and pushing those mountains up. Now this occurs over a very long period of time. It takes a long time for mountains to form and any of these land formations to form, but that is what caused the formation of our mountains. And then in India and Eurasia, we also have the Himalayas, which again are another mountain range. And here's an example of this. So we've got these two continental plates moving towards each other and colliding, and because they are of equal density, they will not be subducted, and therefore they will just push kind of the crust upwards and form our mountain ranges. The last convergent boundary we have to talk about, remember we need to know about all three, are an oceanic convergent boundary. So that's when two plates beneath the ocean collide. Now, when we have this, one of the plates will be subducted underneath the other one. Okay, so subduction occurs at an oceanic as well as an oceanic continental. So for these, features include trenches and volcanic island arcs. And examples include Japan, the Philippines, and the West Indies. Now here's an example of an oceanic boundary. So again, we've got an oceanic crust here and an oceanic crust here, and they are colliding with one another. Now this crust, one of them has to be subducted, okay? So what happens is one of them will be subducted beneath, and just like on land, we will get volcanoes, but because this is happening in an oceanic boundary, the volcanoes will be underwater. So you'll get underwater volcanoes, but you can also get island arcs as well. So when we think about Hawaii is actually formed from these types of boundaries where we get these island arcs. So eventually these underwater volcanoes, if enough magma is pulled up, they will emerge out of the ocean and they will be visible and they will form islands. Something we need to know about is a ridge push. So this is something that helps move plate tectonics. This occurs when the weight of the ridge pushes the rest of the tectonic plate away from the ridge and often towards a subduction zone. So here we've got two different plates that are moving, and as this magma comes up from our mantle and forms our mid-ocean ridge, it will push the plates away from each other. Typically, it'll move them towards a subduction zone here. So we've got this happening kind of in the middle of the ocean, and the plates will be pushed, and here we've got a oceanic continental converging boundary, and here on the other side we have that as well. So the ridge just kind of pushes and furthers that movement of the plates in opposite directions, and they will push them towards the continents. A slab pull is another thing that helps move our plate tectonics. And so at the subduction zone, there's something called a gravity pull or a slab pull. You guys will most likely see it as a slab pull. So this is the weight of the tectonic plate being subducted or pulled below the overlaying plate, and it drags the rest of the plate along behind it. So again, we've got this ridge push that's pushing it out, but then we've got a slab pull here where as this one oceanic plate begins to subduct beneath the continental plate, the gravity of it will kind of force the rest of it along. Okay, so a ridge push is pushing up and out from the middle, pushing in opposite directions, and then a slab pull is pulling the effective gravity, pulling the plate along as it is subducted. So those three were all examples of convergent boundaries. Now we're going to talk about the last type of boundary, which is a transform fault boundary. So in a transform boundary, two plates will scrape past each other. And features include earthquakes and then strike-slip faults, which we will talk about tomorrow. Examples of this include the San Andreas Fault, and they're also found as connectors of mid-ocean ridges. So transform boundaries are a little bit easier because you can just see that they slide past each other. And again, this is where earthquakes are going to form. So what causes the plates to move? So we talked about ridge push and slab pull, but the main driver of plate tectonics, what is causing these plates to actually move on top of the asthenosphere, is actually convection currents. And we talked about this a little bit last week when we looked at the lava lamp in one of our lessons. But the convection current is just the cycle of hot material rising and then cool material sinking. And this will form kind of like a conveyor belt, which will move the plates on top of the asthenosphere. So what happens that heat from the core causes magma to rise to the asthenosphere and move along the boundary of the asthenosphere and the lithosphere. So in that boundary where there is liquid magma, where it's hotter, and then the solid upper portion of the lithosphere. So again, as the magma rises and it gets to the top, there won't be as much heat there. So the magma will eventually cool down. And as it cools, it will become more dense and it will sink back towards the core. Okay, well, once it makes its way to the core, it'll heat up again and it will become less dense and it will rise up. And then as it rises up, it gets away from that heat from the core and again cools down, sinks because it's more dense, right? So this is a slow cyclic movement that causes the plates to move like groceries on a conveyor belt. So this is just a cyclical, so a circle, a cyclical movement that pushes the plates along, okay? And this is what it looks like. These are convection currents. And as we get this movement in the mantle, this is going to push the plates along, right? So as the magma's down here, it's closer to the core. It's very hot. It heats up. It's less dense. It starts to rise to the top. And then as it gets close to the lithosphere, it's away from the heat of the mantle, so it will cool down. And as it cools, it becomes more dense, so it will sink, and then make its way back to the core where it will again heat up. And this cycle just moves these convection currents, which in turn move our plates. And that's all for today. Make sure that your notes are filled in, and if you have any questions, let me know.